we looked at Bernoulli's equation when the fluid was static, in that there was no velocity at any point in the fluid, so we could cancel the terms with velocity in it. We also looked at Bernoulli's equation when the height was constant, so h did not change anywhere along the fluid flow, so the term dealing with h, the potential energy term, could be canceled. Here we're going to look at what happens for this equation at constant pressure. So constant pressure, the pressure doesn't change on either end. The example used in your book, I believe, is a dam, where at the top of the dam of the water, the pressure is atmospheric pressure, but then at the bottom of the dam, they open up a valve allowing the water to shoot out, but that water is also shooting out in air, so there should be an air pressure down there as well. What's the speed at which the water leaves the bottom opening of that dam? So if the pressure at both points is the same, well, we end up with 1/2 rho v1 squared plus 1/2 rho gh1 is equal to 1/2 rho v2 squared plus rho gh2. Every term has density in it, right? The pressures are gone. The pressure didn't have a density term, but the kinetic energy, similar to kinetic energy term, is similar to gravitational potential energy term, all have densities in them. So we can cancel out that density, assuming it's an incompressible fluid, and for water it is. So this would not work well with air as a fluid because air can be compressed, but water is fairly incompressible. I can then rearrange this equation solving for my unknown v2. And I get the following. The velocity at height 2 squared is equal to the initial velocity at height 1 squared plus 2 times the acceleration due to gravity times the difference in heights. Now h1 has to be higher than h2 for v2 to be greater than v1, right? This has to be a positive term, so this whole term is positive, and we add that to the initial velocity. If this is negative, right, if h2 is bigger than h1, then this term becomes negative and the velocity lowers, not rises. So notice the similarity, though, to one of our kinematics equations way back in the earlier chapters, right? Velocity squared, final velocity is equal to initial velocity squared plus 2 times the acceleration times the change in height, or the change in length. So this just reduces down to a very common kinematic equation that we've used before. And this is the effect of Torricelli's theorem, right? What happens to Bernoulli's equation at constant pressure? The other two substitutions, constant height or static, don't really have names associated with them. Now, the last thing your book talks about in this section is the power in the fluid flow, right? Fluid is moving. You can actually use that to transmit power. How much power is in a fluid flow? Well, take Bernoulli's equation, which again is similar to energy. The terms are similar to kinetic energy, potential energy, and so on. And energy is related to work. Work is related to power, right? So this is a density. It's right, mass over volume. This is a density. It's mass over volume. To get these to be energy, we need to multiply them by the volume. Likewise, right, power is work over time. Work is, or energy is a function of time. Work is a function of time. So you have to divide each of these terms by time. So you have to multiply this thing through by volume to get rid of the density terms and turn those into masses. We have to divide this whole thing by time to get power instead of energy. Well, we have an expression of volume over time. That's the flow rate. Flow rate is volume over time. So multiplying Bernoulli's equation by the flow rate gives us the power in the flow. Now, of course, high pressure, high speed, or a large height fluid will have potentially a lot of power behind it, but really it matters what the flow rate is. If there's not much volume flowing through, the power will be small. If there's a large volume flowing through, the power will be great. And we can use that power to, of course, like imagine Niagara Falls, all that water falling off from some great height. As it falls, it increases speed, and you can use that to run turbines to generate electric power.